Hello, it is Renaud Seignoric, Attaché for Science and Technology for the Embassy of France in the US. To celebrate the 5th anniversary of the Paris Agreement, it is my pleasure to welcome Michelle Fehler, an assistant professor from Arizona State University. Michelle holds a Master of Science in Biomimicry and has been teaching several classes on graphic design and biomimicry at the design school. So Michelle, let's face it, very few people are aware of what biomimicry is. So could you give us a consensus definition of what biomimicry is, please?
Yes, thank you, Renaud. Biomimicry is a new discipline based in old traditions to look at nature for finding solutions on how to live on this planet. Now, there are many different examples that are illustrated through the emulation of biomimicry on how to shape something according to a bird's beak or how to design something according to a process in nature. But the essence of biomimicry is really to look into the strategies and to find those functions on how nature does something and then translate those into our own systems. We don't necessarily want to use the organisms for our solutions. So we want to learn from nature and then apply those solutions rather than learning about nature and then using nature for our solutions.
Right, I see. And then, so before going specifically to biomimicry applied to energy, according to you, when should we consider taking a biomimicry approach? Are there specific sectors that tend to use it?
Yes, so historically, biomimicry has really good footing in many disciplines such as industrial design, architecture, construction, and recently it's become a bigger topic in social innovation, business, marketing, chemistry. So as a biomimic, I'm biased. I feel that biomimicry can be applied in any setting in our life because we are part of nature. And so we are earthlings, we're all on the same planet, we all fall under the same rules that any other organism falls under. And so even looking at how we go about our day, how we work, how we spend our time and energy can be biomimetic if we want to learn from the organisms around us. So there is not really a specific time where we shouldn't do biomimicry. I feel that we can do biomimicry in everything we do because we are nature as well.
Very interesting. And so because of the Paris Agreement and because we are based in Houston, we will focus on energy now on. So could you briefly present a few projects using biomimicry related to better energy usage, please?
So we have a couple of projects that are biomimetic that looked at energy. And one example is based off the schools of fish. Now, fish hide in groups in order to protect themselves, but they also have this really amazing solution to save energy. When they swim, each fish, by the movement through the water, creates a little bit of a vortex. And that vortex helps the fish behind it to swim at the same speed without as much energy as would be required if it was swimming alone. And so Dr. Dabiri's lab at Caltech came up with this new method of harnessing wind energy by looking at those vortices and schools of fish. And he is applying a vertical axis turbine that he says is estimated to produce 10 times as much power as a traditional wheel turbine windmill. And it's also less tall. So it's 10 meters tall versus 100 meters tall. So there's a lot of other problems that are traditionally part of the traditional windmills is solved by this height difference. They use less material. They are not in the path of migrating birds. And so overall, it's a very energy efficient and high power at producing solution based off the schools of fish. Then we also have an example that is based off the kingfisher bird and the maple seed. Now the kingfisher bird, as you may have seen or heard, is that the kingfisher can really dive into a body of water, in essence going from one liquid to another, oxygen to hydrogen, and without making a ripple. And it does that because of its shape and it does that because of its shape of its beak. And when it pierces the water, it does not create a great displacement of the liquid. Now the maple seed, when it falls from the tree, is turning like a tornado, creating this uplift, which allows the maple seed to travel a little further away from the mother tree, helping the disbursement in a greater area. And so this company, the Biorenewables, has mimicked these two strategies from nature and applied a retrofit to wind turbines. This retrofit actually reduces the root leakage, which is a phenomena that happens when the air movement is gathering in the center of the windmill, in essence reducing the power produced by the windmill. So the kingfisher idea and the maple seed idea distributes the airflow back into the outer skirts of the blades in a smooth way without causing turbulence, and also uplifting causing some uplift so that it actually has less drag on the wind turbine. And this creates more power and reduced loads on the material of the wind turbine. Then we have another example that is also related to turbines in a certain way, and this is based off the owl wings. The owls, as you probably know, is a predator and hunts at night. And at night, heightened noise levels can sometimes scare away predators. So any bird that flies causes some kind of turbulence in the air, which causes noise. And so the owl cannot afford to scare away its own predators. Plus it needs to be able to rely on its own hearing in order to find the prey. So it needs to fly silent. And the owl does this by having some wings. The leading edge of the wing has serrated textures that break up the airflow. And then the trailing edge of the wing also breaks up the air further. And then any other residual noise is then absorbed by the fluffy down feathers of the owl's wings and legs. So it's truly a silent flight. And this idea was applied to Ziel Abek's turbine because they wanted to come up with a fan that is quieter. And by looking at the owl feathers, they were able to add those serrated edges and the leading edge in order to make the air move in a less noisy way. And they actually reduced the noise level by 6 decibels, which is quite a lot. And it also actually makes it more aerodynamic. So it actually saves energy to run this fan. One other example that I wanted to talk about in terms of energy is based off some organisms in the ocean, namely some fish that move in a form called thunniform, and it's called that because it's based off the tuna fish. And so it's really, imagine the body of the fish is not moving left and right, it's just the end, the caudal fin, the tail fin is moving in a way that moves the fish forward. And some researchers, the BioStream company, looked into tidal power systems that can harness the water moving in and out of the tides to harness this power. And this idea, the same thing, that they're actually, instead of swimming through the water, they are anchored into the ocean floor, and the movable parts are moving so that they actually are then generating power with a generator. And they're also designed so that when there's extreme flows, that they can just let go of any generation and just flow, so they don't get damaged by storms and hurricanes and things like that. And one last example that is based off the swarm logic, which a lot of social insects engage in, which are ants and bees, for example. And this product is based off the bees' swarm logic to create collective behaviors based on simple rules for a decentralized and self-organized system to move towards a greater system. In their case, to build a hive and to find honey and gather food. So Encycle is a company that looked at traditional air conditioning HVAC systems that usually do not talk with each other. If you have a big warehouse and you have 20 air conditioning units, they're all individual and they kick in and off whenever they think they need to kick in and off, normally based off a timer or a thermometer. So in this case, they linked them all together. They made a mesh wireless network to let them communicate through simple rules again, autonomously, but in unison. And so now they can optimize the airflow and the temperature regulation of a greater space together, causing less energy spent and less demand on each of the units. And this result is known as the peak demand shaving.
So beautiful examples that are very diverse and providing engaging applications. And we definitely see how nature has indeed a lot to offer in terms of proven solutions. So thank you. And it makes sense, especially in Texas, which is #1 state in terms of energy production, consumption, but also, and it is less known, #1 in terms of wind energy production. So now my next question will be, actually, because we're celebrating the 5th anniversary of the landmark Paris Agreement, Michelle, what is your climate wish or climate pledge?
If I may have two, I would like to ask that we first of all take a step outside, take a step away from our desks and our computers, and we restore our reconnection to nature, so that we can then get to my second wish, which is to see ourselves as part of this web of life on this planet, and to learn from the genius around us who has solved so many challenges already in so many genius ways, that we can actually live on this planet without damaging it and with still having our lives, just based on those simple rules that nature is providing us. The trick is we just have to look and we have to listen. And while doing so, I would like to ask every person to make going outside into nature, to listen, to hear, to smell, and to observe part of their job description.
Wonderful. Quite a program indeed. Thank you very much, Michelle, for your participation. And I do hope that this will contribute so that people are more aware about biomimicry. Thank you for the various exciting, stimulating examples you provided us, and I wish you a very good day. Thank you again.
Thank you so much for having me. Yes, thank you.
My pleasure. Bye-bye.